Students, now we are going to see is the nuclear reactions of phenol. Okay, we are going to see the nuclear reaction of phenol, which is again very important, and which question chance of coming is more, I'll let you know during the course of this explanation. So now we're going to see the nuclear reaction of phenol. In nuclear reaction of phenol, students, you have to remember that this is your phenol. If something reaction is done to it, something will enter inside the benzene ring, like here, chlorine has entered. So if such thing happens, such is referred as nuclear reaction. In side chain reaction, which we have learned in the previous video, top portion got actions. Now in nuclear, something will enter inside the benzene ring, and that is all about nuclear reaction. So before we learn about nuclear reaction, let us see this structure of phenol. Benzene ring with OH is called phenol. Benzene ring with OH is called phenol. And do remember, in benzene ring, this two position is referred as ortho position. This two position is referred as meta position. And this position is referred as para position. So in benzene, in phenol, these two position is referred as ortho position. These two are meta position, and this is para position. And do remember, phenol is an ortho-para directing group. That means if any compound reacts with phenol in nuclear reaction, phenol will always direct them to come and reside in ortho place or in para place. Ortho or para place. That's why it is ortho-para directing group. But phenol will never ever entertain any functional group to come in meta position, because it is not meta directing group. There are some other functional groups which are meta directing group, but not the phenol. So whenever you do any nuclear reaction of phenol, you have to remember that any functional group enters inside the benzene ring, phenol will direct it to go to the ortho or para position, and it forms ortho-para product. But it never forms meta product because it is not meta directing group. Okay, so whoever comes has to reside in ortho or para position, but not in the meta position, because phenol is ortho-para directing group. So objective question may come here, phenol is which group? So you have to say it's ortho-para directing group, and when any functional group comes inside it during nuclear reaction, it allow it to go in ortho or para place, because it's ortho-para directing group, but not in meta. And who comes and reside in these two places? Electrophile. Electro means electron, phile means loving. So they are electron loving, means electrophiles are electron loving, and that electron loving will substitute the hydrogen present inside in this corner. Okay, and therefore it is called electrophilic. Will substitute hydrogen of benzene ring. You know that here is CH, 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 CH. The hydrogen atom which is out here of phenol will be substituted by the electrophile which comes from outside in the benzene ring. And electrophile means electron loving. And why they love electron? Because they don't have electron. So since they don't have electron, they are electron deficient. That's why they are represented by the sign plus, because they are electron deficient. So do remember, when you do any nuclear reaction of phenol, phenol will allow the electrophile to enter to the ortho or para place. Because it is ortho-para directing group, it will never allow it to go to the meta place. And from here and here, H will be substituted by the electrophile, which is electron loving, will come and reside in ortho or para position. To understand more about this, I would like to show you the resonating structure of phenol now. Students, you can see the resonating structure of phenol out here. So from this resonating structure of phenol, which has been taught in class 11 also, you can see this is called ortho position. This two is called ortho position, this is called meta position, and this is called para. So this is ortho, this is meta, this is para position. So in ortho, meta, para position, if you see during the resonance, this electron which is in phenol will take part in resonance and it will go down, and this pi bond electron will come in the cyclic form. Okay, so you can see the ortho place is electron rich, the ortho place is electron rich, and even the ortho place is electron rich. Can you see any electron in the meta position? No, there is no electron in the meta position. The electron is present either in the ortho position or para position or ortho position. In resonance, ortho position electron is there, meta position, para position electron is there, and in ortho position. So whenever electrophile, which are electron loving, as I said, E plus, will attack where the electrons are more, so it will either attack ortho position or para position or ortho position. Therefore phenol is ortho-para directing group, and electrophile, which are electron loving, will either attack ortho position or para position or ortho position. but it never attacks meta position because there is no electron in the meta position, so it will never ever attack to the meta position. So since electrophiles are electron loving, E plus, they attack the ortho para or ortho place. That's why phenol is ortho-para directing group, we say, students. Students, you came to know that phenol is ortho-para directing group from the resonating structure. So whenever electrophile which are electron loving will attack, they will attack electron rich places like ortho and para. They will never attack meta position, which makes it ortho-para directing group, and it will form ortho or para product, but it will never form meta product. And this electrophile will substitute the hydrogen present out here. So it's a electrophilic substitution reaction, or in general we say nuclear reaction. And these nuclear reactions are of many types, in which in our syllabus we have to learn about three. One is called bromination, one is called nitration, the other is called sulfonation. So there are the three types of nuclear reaction which you have to learn under our syllabus, reduced syllabus: sulfonation, nitration, and bromination. So let us start with the bromination first, students. Now I am reacting for phenol with bromine, water. So we can say bromine water test. This is referred as bromine water test also. Okay, water is acting as a solvent here. So when you react phenol with bromine water, only bromine will react with phenol, not water. Now see from here. From this position, H comes out. From this position also H comes out. From this position also H comes out. That means the H is coming out from ortho and para position, not from meta. Is coming from ortho and para. So how many H is coming out from here? 1, 2, 3. So the 3H will come out. And in place of 3H, from here, 3 bromine will enter in. Okay, in place of 3H, 3 bromine will enter in. So in place of 3H, 3 bromine has entered from here. And this H will combine with 3 bromine to form 3HBr. So how many bromine is used in total? Here is 3. Here is 3. Total 6. So to balance, right here 3. 3 to the 6. Bromine is balanced. And the compound so form is called, count from here. Okay. We have to count from here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So in 2 what is hanging? Bromo. In 4 what is hanging? Bromo. In 6 also what is hanging? Bromo. So 2, 4, 6, total tribromophenol. Benzene ring with OH is called phenol. And this compound called 2, 4, 6 tribromophenol is a white precipitate. So this can be considered as one of the tests for phenol, students. So question: what do you observe when phenol reacts with bromine water? So when phenol reacts with bromine water, we get a white precipitate. And what is the name of this compound? 2, 4, 6 tribromophenol. Again, I am reacting phenol with bromine, but instead of using solvent as water, I am using carbon disulfide. Again, I am reacting phenol with bromine, but this time at ice cold temperature, and instead of using water as solvent, I am using carbon disulfide. Carbon disulfide is also a solvent. So look out here now. When you use another solvent, the reaction will be totally different. When you use bromine water, ortho-para position is attacked simultaneously. Ortho-para position is attacked simultaneously by bromine. But here, when you take carbon disulfide as solvent and maintain ice cold temperature and react with bromine and phenol, that time bromine will not attack ortho-para place simultaneously like this. It will attack separately. So let us consider here are 2 phenols. So here I made 2 phenol. From one phenol I took out H from ortho position, and from another phenol I have to cut H from para position. So total how many H is removed? 2H. One from ortho, one from para. One from ortho, one from para. 2H is removed. And who will go in place of that? Br. Bromine will go. And these 2H will combine with 2Br to form 2HBr. Now total balance it. 2Br, 3Br, 4Br. So 2 2s are 4Br balanced. So students, when you react with water, bromine will attack simultaneously ortho and para position to form this product, which is a white PPT, and the name is 2, 4, 6 tribromophenol. But when you use carbon disulfide as solvent, that time this bromine will not attack ortho para position simultaneously. In one it attacks ortho position, in another it attacks para position separately. And the compound so formed is called, this is called ortho position, so orthobromophenol, and this is called para, this is para position, so parabromophenol. So this is orthobromophenol, parabromophenol, but they don't have any color. But instead of saying ortho, you can count from here 1, 2. So you can say 2-bromophenol. Similarly, instead of saying para-bromophenol, you can say 1, 2, 3, 4. So instead of saying para-bromophenol, you can say 4-bromophenol. Both are same. So do remember and read the question properly when this question comes in exam. If it is bromine water, this is the answer. If it is bromine carbon disulfide, this is the answer. So this is nuclear reaction. Why? Because up portion is remaining same here. OH is remaining OH, but something is entering inside the benzene ring. So that is nuclear reaction. Now we go to the next nuclear reaction, that is nitration. Now here in nitration, we are reacting phenol with dilute nitric acid. Okay, phenol, I am reacting with dilute nitric acid, and whenever we write nitric acid, we write like this: O NO2. This is how you have to break nitric acid. O NO2. O NO2. This is how you break nitric acid. As a result, it is HNO3 only. HNO3. This is how you break nitric acid. So when you react with dilute nitric acid, phenol, okay, this nitro group will enter in, and when nitro group will enter in, that is called nitration. But when you react with dilute nitric acid, it attacks separately. So we again take 2 phenol. In one phenol, take out H from para ortho position, and from another phenol, you take out H from para position. So how many H I have taken? From one from ortho, one from para, 2H. We will go with 2 OH of nitric acid. We will go with 2 OH of nitric acid. 2H from one from ortho, one from para. We will go with 2H. 2H and 2 OH forms 2 water. 2H, 2 OH means 2 water is out. Now here 2 NO2 is left from nitric acid. Out of 2, 1 will go to ortho position, 1 will go to para position. So when you react with dilute nitric acid, phenol, NO2 will enter separately to the ortho and para position, resulting in the formation of these two products, in which this is called ortho position, so orthonitrophenol. This is called para position, so paranitrophenol. Another name, if you count like this: 1, 2, 2 nitrophenol. Another name: 1, 2, 3, 4, 4 nitrophenol. But again, the same reaction, if you do, instead of using dilute nitric acid, if you use concentrated nitric acid, instead of dilute, if you use concentrated nitric acid, and if you use the catalyst like concentrated sulfuric acid, and if you heat at 80 degrees Celsius, okay students, 60 to 80 degrees Celsius, 60 to 80 degrees Celsius if you heat it. Now look out here, earlier when you react with dilute, NO2 attacks separately, but when you react with concentrated nitric acid using Kong sulfuric acid as catalyst, dehydrating agent, actually it is, at 60 to 80 degrees Celsius. Again we take here 3 nitric acid, and how we write nitric acid, I have already mentioned: ONO2, HNO3, HNO3, nitric acid, yes, and we have taken 3 molecules, so I'll write here 3. So when you react with dilute, NO2 will attract separately to the ortho and para, but when you take concentrated nitric acid using Kong sulfuric acid, okay, it will attack ortho para simultaneously. So from this phenol, take out H from ortho position, take out H from para position, take out H from ortho position. So how many H is removed total? 3H. So that 3H will combine with 3OH to form 3 water, 3H, 3OH, 3 water. Now here is 3 NO2 left. So this 3 NO2 will go here. One NO2 will go here. The other NO2 will go here. The other NO2 will go here. But when you write NO2 here, first write N, then write O2. So you get 3 NO2 out here. Okay, so 3 NO2 has entered here, here, and here, and they are entering into the ortho and para position, but not to the matter, because phenol is ortho-para dielectric group, not matter. As a result, the compound so formed is called, count from here: 1, 2, 3, 4, 5, 6. 2, 4, 6 trinitro. 2, 4, 6 trinitrophenol. 2, 4, 6 trinitrophenol, which is more popularly known by the name picric acid, and it is an explosive. So this question 10,000% sure, this question is 10,000% sure, it will surely come in your board exam. 10,000% sure this will come. And listen to the question now, how it may come. The product form when phenol reacts with concentrated nitric acid, concentrated sulfuric acid at 60 to 80 degrees Celsius. 4 option, you will take it in picric acid if it is given this as option, or you will take it in 2, 4, 6 trinitrophenol, or you can take it in a compound which is explosive. So this is more important than this. So if you see out here students, in bromination both are important, whereas in nitration more than first, second one is more important. So we finished 2 nuclear reaction of phenol now. Now the last nuclear reaction of phenol is this one, sulfonation students. So in sulfonation, we react phenol with sulfuric acid using heating at 80 degrees Celsius. So in sulfonation, we have to react phenol with sulfuric acid using 80 degrees Celsius. Okay, now sulfuric acid, when you break, we break somewhat like this, OSO3H. This is how you have to break sulfuric acid, students. You can see here, H2, H2, SO4. This is how you break sulfuric acid. And here, this is called sulfonic acid group, which contains 5 atoms, 1, 2, 3, 4, 5. Therefore, it will not attack ortho and para position simultaneously. It will attack separately. So let us see how it attacks. So you take 2 phenol. So one phenol is here, the other phenol is here. So from one phenol I have taken H from ortho position. The other, from another phenol I have taken H from para position. You take 2 sulfuric acid, so you get these 2. So take out H from ortho, take out H from para. So there were 2H which is out from here will go with 2OH of sulfuric acid. 2H and 2O forms 2 water. 2H and 2OH will form 2 water. Now here we have 2 SO3H, out of which 1 SO3H will enter here and 1 SO3 will enter here, and we get sulfonation product. Okay, and here we get 2 products, one this, along with water as the byproduct. Hope so you understood. If you not, you can repeat the video. Now student, what is the name? Do remember, in these 2 cases, this will get preference. So its name should be at the back. So we say benzene sulfonic acid. You can see here benzene sulfonic acid, benzene sulfonic acid, and we replace these 2 positions. This will go up, this will come down. So if OH comes here, the name will be orthohydroxy. Orthohydroxy. Replace the place. Take this up, this down. So OH comes in ortho position. So we say orthohydroxy, benzene sulfonic acid. Similarly, you replace the position of these 2 because this gives preference. So this will come in the para position. So we call para hydroxy, benzene sulfonic acid. But instead of ortho, you can write 2-hydroxy benzene sulfonic acid. Similarly, in place of para, you can write 4-hydroxy benzene sulfonic acid. So by this, we come to the end of nuclear reaction of phenol. And do remember how the question comes from here. So when phenol reacts with concentrated sulfuric acid at 80 degrees, the product form is these 2. Okay. Now, do remember there are 2 products, which is the major and which is the minor product out here. So always remember, the one which is far away are stable. So we consider para as the major product. The one which are near, there will be electronic repulsion among them due to steric hindrance. Electronic repulsion is called steric hindrance. So in ortho position, functional groups are nearby. So electronic repulsion occurs, steric hindrance will be more. So it is unstable. So it is minor product, forms in less amount. They are far apart. So steric hindrance will be less, electronic repulsion will be less, there will be major product. So in ortho and para, always major product is para, minor product is ortho. Same way here also, the major product is para, minor is ortho. Same way here also, major is ortho, para, minor is ortho. Okay, product. And to remember, out of this all nuclear reaction of phenol, the most important one is this one. When phenol reacts with conc nitric, conc sulfuric 60 to 80, you get picric acid, which is an explosive compound. 10,000% sure it may come. So by this, we come to the end of nuclear reaction of phenol. So we have finished side chain reaction of phenol. Now we have finished nuclear reaction of phenol. In my next video, we will learn special reaction of phenol. And after completing special reaction of phenol, chemical property will be get over. Physical property get over. Chemical property we have finished. We'll be finishing after doing special reaction. Then we go to the test for phenol. Thank you very much.